Hello, my kiddos and my kiddas. We are looking at domains. Overall, we are looking at asymptotes. One of my very, very favorite things, mostly because of how the name sounds, which probably is not why I should like it, but I really do. And it's just a fun thing to say, asymptote. And you always have to say it in that accent. Otherwise, it's not as fun. It's just asymptote. And that just sounds really boring and then just kind of like, meh. So we are looking at domains. And so when we're looking at rational functions, which is where we have our asymptotes, or most of our asymptotes, um, we can plug in any number for our x value except for whatever would make our denominator 0. So then in this case, I have a denominator of x squared minus 9. So I want to figure out what is going to make this denominator equal to 0. So I could always factor it. Because it's a difference of squares, I end up with x plus 3 and x minus 3. And then I would separate these two since they're both equal to 0 and set them equal to 0. So here I have two situations where my x would end up being 0 if I plugged in these x values, or my denominator would be 0, sorry. And so that means that my domain is anywhere except for where x is positive or negative 3. So when we have these areas where we cannot divide by, or we can't plug in a certain number because we would be dividing by 0, this creates a vertical asymptote. So it's whatever x value or values that make the domain equal to 0. And so we also have horizontal asymptotes. So again, vertical asymptotes, these are the up and down lines like this. So they're kind of dotted and imaginary because they're not a part of the graph itself, but it's kind of like an invisible barrier that you cannot cross. So when it comes to horizontal asymptotes, we're looking at ones that go like this along the horizon. Again, they are not really there. They're just a line that you cannot cross. So we represent them with dotted lines. So if I have some function where I have something that looks like a function on top and a function on bottom, so this could be something like x squared minus 9, and then x squared plus 4x minus 2, any of these kind of situations, but we have something like a function, something that could be its own function on top and on bottom. When we have horizontal asymptotes, if the degree of whatever's on top, so the degree of the numerator, is greater than the degree of the denominator, and by degree I mean the highest exponent, then that means that there is no horizontal asymptote. So if we have a higher exponent on top than we do on bottom when it comes to these rational functions, then we would have no horizontal asymptote at all. It just doesn't exist. We don't have one. If we have a situation where the numerator is smaller than the denominator, meaning the degree or the exponent, then our horizontal asymptote is going to be where y is equal to 0. So basically, we can't cross the x-axis. We have a dotted line there that is an asymptote that we cannot touch. You don't touch your asymptote, you don't touch someone else's asymptote, and you definitely don't touch the asymptotes on the graph. No consent has been given. And then we have our last one. So if the degrees on the denominator and the numerator, if these are both the same, so say we have x squared over x squared or x cubed over x cubed, and those are the highest exponents, then we are dividing our leading coefficients. So we take the leading coefficient of the top and we divide it with the leading coefficient of the bottom, and it's that y equal 2 line. So then a way that I help remember this is Bobo button eats DC. So the Bobo part is saying that if my exponent is bigger on the bottom, then its y is equal to 0. The bottom, if it's bigger on top, then there's none. And then with my eats DC, if the exponents are the same, we divide the coefficients. And so it's y is equal to whatever the division of the coefficients are. And so I have it written again here. So if it's bigger on the bottom, asymptote is 0. So y is equal to 0. And of course, bigger on bottom, we're talking about the exponents. If the exponents are bigger on top, there is no asymptote. And if our exponents are the same, then we're dividing the leading coefficients. So I'm going to do these first three with you guys just to give you an example, and then the last three I will save for my bebes. So they want us to find both the vertical asymptote, which I'm going to abbreviate because I'm a math person and I hate spelling, to VA, and our horizontal asymptotes at HA. So remember, vertical asymptotes, we're looking at the denominator. So we're trying to figure out when this denominator is going to be equal to 0. So then here we would have a horizontal asymptote where x is equal to 2. So we'd move over to the right where x is 2 and create a vertical dotted line, like something like that. And then when it comes to our horizontal asymptote, again, we're looking at our exponents. So here on top, I have a highest exponent of 2. On the bottom, I have an exponent of 1. Our exponent is bigger on top. So bigger on top, that means I'm doing the bottom, which means bigger on top, I have no exponent, or sorry, not no exponent, no horizontal asymptote. So whenever I ask myself these, is it bigger on top, bigger on bottom, or are the exponents the same? So that helps us with the Bobo, bottom, and eats DC. Next one, again, I'm doing the same thing. I'm going to check out my vertical asymptote first. I'm setting the denominator equal to 0. And then look, I'm done. That's as far as I can go. So my vertical asymptote is actually my y-axis. And then I'm looking at my horizontal asymptote. So I have a highest exponent of 1 on top and 1 on the bottom. So this means that my exponents are the same. So that's my eats DC. So that means I'm dividing the coefficients. So the leading coefficients, I have a 1 and a 1. So my horizontal asymptote would be dividing those coefficients, which is just equal to 1. And then I'm done. And then this last one, again, I'm finding what is on the bottom first. That tells me my vertical asymptote. So here I end up with 2 vertical asymptotes. One at where x is equal to -3 and one where x is equal to +1. Anytime we have a vertical asymptote, we do end up having a pause for our horizontal. So in between those, it would pause and then continue again. So anything that's between these vertical asymptotes is actually fair game to cross. I also have to find my horizontal asymptote, speaking of. Again, I'm looking at my exponents. I have a 1 on top and a 2 on bottom. That means my exponent on the bottom is bigger, so bigger on the bottom, which is Bobo. And so that means that my horizontal asymptote is going to be where y is equal to 0. Last thing I'm going to look at is, okay, what if we have situations where we have real life representations? So the first one, the cost is in millions of dollars of removing a P% of industrial and municipal pollutants into the river is given by this first equation or function. And so this is when P is greater than or equal to 0 but less than 100. So they want us first to find the slots of removing 20% and then 45 and then 80. So basically they just want us to plug this in for P. And we'll do this 3 times. I'm going to do it rather quickly because I don't think it's that difficult to just plug in. And I know my kids are really good at just plugging in numbers and simplifying. One thing that I totally forgot, and I know my students are like, oh my gosh, Miss Lloyd, what are your units? Because I yell at them all the time. Well, maybe not yell, but I sternly talk to them whenever they forget their unit, saying, is this 56.25 tacos? I don't feel like it is, especially if you have 0.25 of a taco. Quarter of a taco? That just sounds really gross. What happened to the other 3/4? Did someone eat it? Are you eating the rest of someone else's taco? I mean, like, you're desperate for tacos, that's fine, but like, So here they said at the very beginning that this is in millions of dollars. So I want to make sure that I have those labels. Now that I found how much it's going to cost for me to take out this percentage of pollutants, they then ask me, according to the model, is it possible to remove 100% of the pollutants? So one, this is a great reason as to why we shouldn't pollute at all or throw things into our environment that shouldn't really be there. Because really we can't ever take out 100%. There's always going to be stuff somewhere and it's really bad for us and it's never really going to go completely away. So we should just not do it. It's not good for the environment. So also, if I were to plug in this 100 into the P that we started off with, I would end up in the denominator with 100 minus 100, which would give me 0. We would be dividing by 0 and that makes the world explode. And so not only can we not divide by 0, but also some of the stuff just can't be taken out. And then this last example I'm going to save for my students. And so that's all that I have for you guys over in YouTube land. If you found this helpful, then please like and subscribe. And if you think that this could help someone else, please feel free to share it. Spread that love.